Okay, day four is about two things that you maybe have never heard of. So two new ideas, but I don't think they're super difficult. I think one of them you probably have used, you just didn't know it by this name. But these are, we're going to talk about what's called conditional probability, and we're going to use contingency tables to find conditional probability on some of them. So our learning target is I can find the probability that one event occurs given that another one has already occurred. So that's what conditional probability is. You're trying to find the probability based on the condition that something else has already happened. And then I can use tables and tree diagrams to determine. So tables are contingency tables. So conditional probability, the probability that event B will occur given that A, another event, A, has already occurred. So for the most part on this one, we're talking about like, you see in the example here, male, female, right-handed, left-handed. We want to know the probability of, say, being right-handed given you're a female. So that event happened at birth, and then over here we're doing right hand, left hand. Okay. So yeah, let's talk about it. So the formula for this, instead of dividing by everybody, you just want to divide by the people who met that first condition, that A condition. So for any two events, this notation right here, the probability of B given A, means the probability of all those who were A and then followed up with B divided by all those who met the A condition. So it's just, instead of dividing by everybody, the whole group, you're going to divide by just the people that met the first condition. Okay? So we often use contingency tables, which are just a fancy name for a two-way frequency. So it's got two different variables here. You got left hand and right hand, and you got gender going the other way. It organizes the data based off those two variables. So how you read this table, well, we're just going to answer some questions. Let me say it that way, and then we'll see how to read the table from this. But basically, just there's 100 people, and 87 of them are right-handed, 13 are left-handed. 52 are male, 48 are female. And then it also breaks it down by 43 are right-handed and male, 9 are left-handed and male, and so on. So use the table to the right, answer the following questions. How many people are represented in this survey? So you notice right-handed, left-handed, there's 87 and 13, that adds up to 100. Male and female, that adds up to 100. That's because that's how many people are there. This has to be true. If they don't both add up to the same number, then you collected your data wrong. So this represents 100 people. Now, how many are female? Well, there's 44 right-handed and 4 left-handed, but there's 48 total female. So there's 48 female. How many are male? 52. How many are right-handed? Well, I'm going to go to the right-handed column. The total number of people who are right-handed is 87. Total number of people who are left-handed is 13. Okay, so that's kind of how you read it. Now let's do some probabilities here. So what's the probability of being right-handed? So basically, we're just going to look at, out of how many. So how many of them are right-handed? Well, there are 87 out of 100. So the probability is 0.87. How about female? Well, there's 48. So it'd be 48 out of 100 equals 0.48. Because notice, I'm just saying the probability of being right-handed. That's not conditional at all. That's just out of everybody. How about the probability of being male and right-handed? That's still out of everybody because there's no conditional part here. We didn't say given in here. So male and right-handed is 43 out of the 100 people. So that's 0.43. Female and left-handed, see, female left-handed would be 4 out of 100. So that's 0.04. So these kind of questions are not conditional. These are just out of everybody, out of the whole group, out of the 100 people there are. Now down here, finding conditional probability, and maybe I'll zoom out here so we can see everything all at once. So we see the question and the table at the same time. What's the probability of being right-handed given that you're a female? Okay, so we need to first figure out how many right-handed females there are. And we're going to divide it by how many females. So out of all the females, how many of them are right-handed? So the probability of being right-handed and female, but we're going to divide by the females. Now I say probability here, we could also do the number of, so just how many people. So either way you could do this. And well, I'll show that in a second. So right-handed and female. So right-handed female is 44. Now that's out of all the females, which is 48. So 44 of the 48 are right-handed. The females are right-handed, so that's 0.917. Now we could have, if we did the actual, because this was the number of, if we did the actual probability, R and F, right-handed female, was 44 out of 100, so that's 0.44. So 0.44 divided by, again, 48 of them, your probability of being is 48, so 0.48. I still get the same answer. So you can do the number of or the probabilities, even if it's not out of 100. If it was out of a different number, it wouldn't be just 44. 44 wouldn't convert to 0.44, but the probabilities when you divide them would be 0.917 either way. Female and right-handed, now is that going to be different? Because this is right-handed given female, this is female given right-handed. Does that change things? Well, we're still going to have the same top number, so female and right-handed, but now we're going to divide it by all the people who are right-handed. So that's a different question than given female. This is given your, so out of all, we basically took all the right-handed people, put them in a group, and said, how many females are there? So females and right-handed, there's 44. There's 87 who are right-handed. So that's 0.506, which kind of makes sense. Of all the right-handed people, half of them would probably be female, because about half the population is female. Just a little bit more, I think, because the actual data, there's a few more females than males on planet Earth, but we'd expect to be pretty close to 0.5. So what's the probability of being left-handed given male? We expect this to be pretty low because not many people are left-handed, but we need to figure out so the probability of being left-handed and male divided by, it's just going to be out of how many males there are. So this would be 9 out of the 52 males, which is 0.173. Now, how about what's the probability of being male given you're right-handed? Well, I'm assuming if I took all the right-handers and I said how many are female, how many are male, it's probably going to be about 50%, pretty close to it. Let's find out. So male and right-handed divided by right-handed. So male and right-handed is 43. It's 43 of them. If I look up how many are right-handed, there are 87 people who are right-handed. Divide that out, you get 0.494. So it kind of makes sense that if I add those up, that's everybody. So what's the probability of being female given you're right-handed, or the probability of being male given you're right-handed? This is out of all the right-handers, you're one or the other. So we're going to classify as one or the other. So that should add up to 1. That's everybody. Okay, so we'll flip this over. I spilled some coffee on the table. So using a tree diagram, we actually use a tree diagram to help us out with some more difficult questions. So if I just read these questions to you, it might seem like it's going to be really hard to answer that. But if you use a tree diagram, it gets kind of easy. So a school system compiled the following information from a survey it sent out to people who were juniors 10 years earlier. So 10 years ago, they were juniors. 85% of the students graduated from high school. Not a very high-achieving school, but of the students who graduated, 90% were happy with their present job. Of the students who did not graduate from high school, 60% are happy. What is the probability that a person from the junior class 10 years ago graduated and is happy? So that's out of everybody. Out of everybody, what's the probability of meeting these two requirements? Well, it's kind of hard to answer that, but if we make a tree diagram, it does make it a lot simpler. So we're trying to figure out what's the probability that they did graduate. I'll say G means they did graduate, and I'll say H stands for happy. Well, we learned that if two events are independent, you just multiply them together. Probability of G times the probability of H. Are these independent, though? So does the fact that you graduated affect whether or not you're happy? If you did graduate, you're 90% likely to be happy. If you did not, you're 60. So that does affect it. In this survey, these are not independent events. Graduating makes you more likely to be happy with your current job. Well, that means that instead of just taking probability of G times the probability of H, I'm going to take the probability of G times the probability of H given G. So that's my probability, or that's what I multiply together to find out the overall probability of both these events happening. So So first off, the tree diagram, I kind of drew it for you here to make branches. So 10 years ago, they either graduated or they didn't. So they graduated or they did not graduate. And now 0.85 did, that means 0.15 did not. They didn't tell us that, but we can assume. Either you did or you didn't graduate. Of those who did graduate, the branches are happy, not happy. And then the ones who did not graduate, they are either happy, happy or not happy. But these are different. If I did graduate, 0.9. 0.90 is a probability. Whereas not happy, that means 0.1. So I can assume the rest. So if 90% are happy, 10% are not. If I did not graduate, there's a 60% chance, or 0.6, which means it's a 0.4 chance that I'm not happy. I put a 0 here. We can skip it if we want. I'm going to put them in all of them to make it consistent. So that means with a tree diagram, if I want to find all of these branches, I need to multiply these together. So the probability of graduating and being happy, so this is a probability of graduating and being happy, I'm going to multiply 0.85 times 0.9, because this is the probability of being happy given you graduated. So this 0.9 goes right here. This is 0.85. So it's literally what we're doing here in all these branches. So if I take all of these and multiply them together, I can find all my outcomes. Okay, so this one is 0.765. So I can put on the end of this 0.765. If I do all these branches, these should add all up to 1, because these are all the things that could happen. The sample space is graduate happy, graduate not happy, not graduate happy, not graduate not happy. So although everyone did one of those, so all of these need to add up. So if I multiply all these together, like I'll take 0.85 times 0.1. This branch right here is 0.085. 0.15 times 0.6. This branch is 0.09. 0.15 times 0.4. This is 0.06. Now if you add all those up, so 0.765 plus 0.085 plus 0.09 plus 0.06, you get 1. That covers everybody. So you're in one of these categories. Now, what is the probability that a student from the junior class 10 years ago did not graduate and is happy? Did not graduate and is happy, 0.09. So the probability of not graduate and happy going to be the probability of not graduate times the probability of happy given not graduate. So this is 0.15. This was 0.6. Well, my tree diagram kind of took care of all this for me. So I could skip a little bit there, but I just laid it all out here. Now, are the events described above, so graduating high school, whether or not you graduated, and your happiness at a current job, are they independent? Kind of already answered this. Okay, so did graduating affect your happiness? Absolutely. Of the people who graduated, 90% are happy. The ones that did not, only 60%. So these are no. I'm going to write this out and I'll read it. So no, because the probability of being happy, you can think of it as going up if you graduate or going down if you did not graduate. Or you just say it just depends on it, because it's one value if you did graduate, a different value if you didn't. Okay, now, different kind of questions here. So you could do it. A lot of times they'll give you all this information. You don't necessarily need to make a tree diagram. You can try if you want. This one's a little bit harder to make a tree diagram. All the information you need is basically there. So it says, using the information to the right, find the following probabilities. So just kind of read through it. It says 39% have a pet now and have had a pet in the past. So that's an and statement. 61% do not have a pet right now. 86% have a pet right now. 14% do not have a pet and have never had a pet. I'm not sure how I have never had a pet. So there's a lot of statements here. So a randomly chosen respondent, what's the probability that they has a pet currently, given the respondent has had a pet in the past? So on this one, with the probability that it has a pet, say, well, maybe I'll just write it out because this gets old. So has a pet given they has had a pet. That would be the probability of both. So probability of has pet and has had divided by, and then this goes on bottom, the probability that has had a pet. So the probability that they, both of these, is 0.39. So if I can fit this in, maybe I'll just go like this. I'll drop it down here. So 0.39, because that's probability. And again, these aren't numbers. These aren't the frequencies. Like on the front side, we were able to do frequencies on this and just divide the frequencies. We can also divide probabilities, and it works just the same. We have no idea what this is out of. We know 39% or 0.39. And then, let's see, 86 have had a pet. Have had. Boy. So has had or have had, same thing. So 0.86. So this would be 0.453. A randomly chosen respondent has never had a pet, given that the respondent doesn't have one now. So maybe they, let me get this straightened out. Let's say they may have had one in the past and don't have now. That's what could have happened. But these people, they don't have a pet and they've never had a pet. Okay? So the probability of, we'll say, never had, given that they don't have, so it doesn't have. So it's going to be the probability of both. The probability of never and doesn't divided by doesn't. Okay, so never and doesn't is 14, so 0.14, and the probability that they don't have one right now, 61% don't have a pet right now, so that's out of 61, so it'd be 0.230 for that one. Okay, so yeah, that one's, the wording was difficult, but the math part wasn't so difficult on that one. So just remember, with conditional probability, you're not dividing by everybody, you're dividing by the given condition. Whatever is given, the probability of that given, that's what you're dividing by.